Good morning, all of you. Today we will start UML diagrams, UML, Unified Modeling Language. Okay, so this is your syllabus. We have completed section first, that is 4 chapters, and from section second, we have completed unit 7, unit 8, that is 2 chapters, and 2 chapters are remaining from section second. So these 2 chapters are related with UML diagrams. So fifth chapter is behavioral modeling using UML, and sixth chapter is architectural modeling using UML. So this is your syllabus for fifth chapter and sixth chapter. So in fifth chapter we will see, in behavioral model we will see interactions, use case diagrams, interaction diagrams and activity diagrams, events and signals, state machines, processes and threads, time and space, state chart diagrams. For this syllabus, a textbook is the Unified Modeling Language User Guide by Grady Booch, James Rambag, Ivor Jacobson by Addison Wellesley. For this chapter, your CO is list the object of unified modeling language for a given problem statement. So before starting the UML chapter, so UML modeling, there are some users, use cases, interactions, activities. So we will study use case diagram, interaction diagram, activity diagrams, events, signals. These are the whole chapters. This single point is a single chapter of a book. So there are nearly about 10 points. So 10 points consist of 10 different chapters. So interaction is a different chapter, use case is a different chapter, use case diagram is again different chapter. So each point have a different chapter in your book. So we'll study one by one in detail. First, interaction. In this part, we'll study roles, links, messages, actions, and sequences. Modeling flow of control, creating well structured algorithms. So, every interesting system object don't just sit idle. They interact with one another by passing a message. An interaction is a behavior that comprises a set of messages exchanged among set of objects within context accomplish a purpose. So you use interactions to model the dynamic aspect of collaborations, representing societies of objects playing specific roles, all working together to carry out some behavior that's bigger than the sum of the elements. These roles represent prototypical instances of classes, interfaces, components, nodes, and use cases. Their dynamic aspects are visualized, specified, constructed, and documented as flows of control that may encompass simple sequential threads through a system, as well as more complex flows that involve branching, looping, recursion, and concurrency. You can model each interaction into two ways by emphasizing its time ordering of message or by emphasizing its sequencing of messages in the context of some structural organization of the objects. So well structured interactions are like well structured algorithms, efficient, simple, adaptable, and understandable. So in the UML, you model the static aspects by system by using such elements as class diagrams and object diagrams. These diagrams let you visualize, specify, construct, and document the things that live in your system, including classes, interfaces, components, nodes, and use cases and their instances together with the way those things sit relationship with one another. In UML, you model the dynamic aspects of system by setting interactions like an object diagram. An interaction statistically set the stage for the behavior by introducing all the objects that work together to carry out some action. So going beyond object diagram, however, interactions also introduce message that is dispatched from object to object. Most often, messages involve the invocation of an operation or sending of a signal. Messages may also encompass the creation and destruction of the other object. You use interactions to model the flow of control within an operation, a class, a component, a use case, or the system as you can reason about these flows into two ways. So first, you can focus how messages are dispatched across the time. And second, you can focus on the structural relationship among the objects in an interaction and then consider how messages are passed within the context of that structure. So the UML provides graphical representation of the message as shown in the figure. The notation permits to visualize a message in the way that you let's emphasize the most important parts by its name, parameter, and the sequence. Graphically, a message is rendered as directed line almost always includes the names of its operations. Here example is given as air traffic planner. So message to flight plan. So this is the object air traffic planner have object T. So colon represents as object. This is the link. Then this is the another object. So get position at time T. So this is the message. Get position from air traffic planner to the flight plan. Send a message as a get position at time T, and this one indicates that a sequence number of that message. So here 1.1 indicates that this acknowledgement or message regarding 1 gives the answer get last checkpoint. This is the message given by flight plan to flight plan itself. So this is links and sequencing. So every object have a link from one object to another object with sending a message, and every message have a sequence number. So, what are the terms and concepts regarding the interactions? An interaction is a behavior that comprises a set of messages exchanged among the set of objects within a context to accomplish a purpose. And what is a message? A message is a specification of communication between objects that conveys the information with the expectation that activity will ensure. So, what is the context? You may find an interaction wherever objects are linked to one another. You will find interactions in the collaboration of objects that exist in the context of your system or subsystem. You may also find interaction with the context of an operation or the context of class. Most often, you will find interaction in the collaboration of objects that exist in the context of your system or subsystem. So, an interaction may also found in the representation of component, code, or use case, each of which in the UML is a really a kind of classifier. In the context of a use case, an interaction represents a scenarios that in turn represents one thread through the action of the use case. So, what are the objects and roles during the interactions? The object that participate in an interaction are either concrete thing or prototypical thing. As a concrete thing, an object represents something in the real world. For example, P is instance of class person might be done particular human. Alternatively, prototypical thing P might represent instance of person. That is what distinguishes in collaboration. In a collaboration, objects you find the prototypical thing that play particular roles, not a specific objects in the real world. In the context of interaction, you may find instance of classes, components, nodes, and uses. Although abstract classes and interfaces by definition, you may not have any direct instances. You may find instances of these things in an interaction. An interaction goes further by introducing a dynamic sequence of messages and that may pass along the link that connect these objects. So what is a link? Link is a semantic connection between the objects. In general, link is an instance of association. This figure shows wherever the class has an association to another class, there may be a link between two instances of the classes. Wherever there is a link between two objects, one object send message and to another object. See here class person. Person may be employee, may be boss. Okay, so it have a components or parameters like set compensation, yes for salary, assigned D for department. So this person class sends, this is known as employee, and this company is known as employer. Company is another class. So one class sends a message to another class. So there is a link between two classes. So person P, company C, so assigns a department. Company assigns a department to that person, and this is known as a link. This is known as a link. When two classes associated with each other, when two classes are there, there is association between two classes, then there is a link between their object or instances. See the figure carefully. So a link specifies a path along which one object can dispatch a message to another object or same object. Most of time it is sufficient to specify that such a path exists. If you need more precise about how the path exists, you can adorn the appropriate end of link with any of the following standard stereotypes. So association indicates specifies the corresponding object to the visible association. Self indicates self indicates or specify that the corresponding object is visible because it is a dispatcher of the operation. Global specifies the corresponding object is visible because it is in an enclosing scope. Local specifies the corresponding object is visible because it is in local scope. Parameter indicates or specifies the corresponding object is visible because it is a parameter. So, an instance of an association, a link may be rendered with the most of adornments appropriate associations such as name, association role name, navigation, and aggregation. Multiplicity, however, does not apply to links since they are instances of an association. Then what is a message? Suppose you have a set of objects and set of links that connect those objects. If that's all you have, then you have completely static model that can be represented by object diagram. Object diagram model the state of society of objects at a given moment in a time and are useful when you want to visualize, specify, construct, or document a static object structure. A message in the specification of communication among the object that conveys the information with the expectation of activity will ensure the receipt of the message instance may be considered as instance of an event. When you pass a message, the action that results is an executable statement that forms the abstraction of the computational procedure. An action may result in the change in state. So in UML, you can model several kinds of actions. such as call, return, send, create, destroy. So call invokes an operation. An object may send a message itself, resulting in the local invocation of an operation. So return returns a value to the caller. Sends the signal to the object. Creates an object. Destroys the object. An object may commit suicide by destroying itself. So messages, you can model complex action in the UML as well. In addition, the five basic kinds of actions listed above, you can attach the arbitrary strings to a message in which you can write complex expressions also. So UML does not specify syntax or semantics of such strings. So UML provides a distinction among these kinds of messages as shown in the figure. So there is a communication between, see in this figure, there is a communication between client, planning assistant and ticket agent. And this C, T, P, these are the objects. So object communicate to each other. So client sends a message as a create to the ticket agent. So it have then again send a message with some parameter. So ticket agent calculate route. There is a call, that is local invocation call itself again. Then return value as a route. If it is not okay, then destroy, and client communicate with the planning assistant to notify, send a message. So the most common kind of message you will model is a call, in which one object invokes an operation of another or the same object. An object cannot just call any random operation. If an object such as C in the example above, in given example, call the operation set it itinerary on the instance to the ticket agent, the operation set itinerary must not only be defined the class ticket agent. That is, it must declare in the class ticket agent or one of its parent. It is must also the visible to the caller C. Then sequencing, when object passes the message to another, in effect delegating some action to the receiver, the receiving object might in turn send a message to another object, which might send a message to yet a different object, and so on. This stream of messages forms a sequence. Any sequence must have beginning. The start of every sequence is rooted in some process or thread. Furthermore, any sequence will continue as long as the process or thread that owns it lives. A non-stop system such as you might find in the real-time device control will continue to execute as long as node it runs on is up. Each process and thread within a system defines a different flow of control, and within each flow, messages are ordered in a sequence by time. To better visualize the sequence of messages, you can explicitly model the order of messages relative to the start of the sequence by using a solid arrow head sequence by prefixed the message with a sequence number. So most commonly you can specify using a solid arrow. So here in this figure, a message sent view to controller, controller to cache. So each message have a sequence number. So check at p, this is the message and message have number 2, this is a sequence number. Then so the controller check itself, that is that message 2.1. So find at p, this is nested flow, and put receipt recent peak, this is the message from controller to cache. You can draw any example not from these, you can take any example. Okay, so in this case the message find at is specified in the first message nested. Find at is nested message, okay, call itself again, whereas the second message is sequence. This is the sequence message from view to controller, controller to cache. Then less common but also possible, you can specify flat flow of control rendered using a stick arrowhead to model the non-procedural progression, make control from step to step. In this case, the message assert call is specified as the second message in the sequence. So see, there is message sequence number 1, message is handshot. So this one is sequence number. Similarly, 2 is also sequence number. So this is known as flat flow control, and the message say handshot or assert call. These are the messages from caller to telephone, telephone to exchange, respectively. So the distinction between flat and procedural sequential is suitable and is really in an advanced modeling issue. Typically, you will use flat sequences only when modeling interactions in the context of uses that involve the system as a whole together with the actors outside the system. Such sequences are often flat because control simply progresses from step to step without any consideration for nested flows of control. In just about all other circumstances, you will want to use procedural sequences because they represent ordinary nested operations, calls of the type you find in the most programming languages. The next, creation, modification, destruction. Most of time, objects you show participating in an interaction exist for the entire duration of interaction. However, in some interactions, objects may have created that is specified by create message and destroyed that is specified by destroy message. The same is true of links. The relationships among objects may come and go. To specify if an object or link enters or leaves during the interaction, you can attach one of the following constraints to the element. So there are 3 points: new, distant, and destroyed and transient. So new specifies that the instance or link is created during the execution of enclosing situation or enclosing interaction. Destroyed specifies that instance or link is destroyed prior to the completion of the execution of the enclosing interaction. Transient specifies the instance or link created during the execution of the enclosing interaction, but it is destroyed before completion of the execution. So during interaction, an object typically changes the values of attributes, its states, or its roles. So you can represent the modification of an object by replicating the object in the interaction with possibly different attribute values, state, or roles. On a sequence diagram, you had or you should place each variant of the object on the same lifeline. In an interaction diagram, you should connect each variant with a become message. So what is the representation? When you model an interaction, you typically include both objects and messages. So object, each of one playing specific role, and messages, each one representing communication between objects with the some resulting action. So you can visualize these objects and messages involved in an interaction in two ways: by emphasizing the time ordering of the messages and by emphasizing structural organization of objects send and receive the messages. So in UML, the first kind of representation is called a sequence diagram and second kind of representation is called as collaboration diagram. Both sequence diagram and collaboration diagrams are kinds of interaction diagrams. Sequence diagrams and collaboration diagrams are largely isomorphic, meaning that you can take one and transform it to another without loss of information. So there are some visual differences, however. First difference is a sequence diagram permit you to model a lifeline of an object. An object's lifeline represents the existence of the object at a particular time and possibly covering the object's creation and destruction. Second is collaboration diagram permits you to model the structural links that may exist among the objects in an interaction. So what is a modeling flow of control? So most common purpose for which you shall use interactions is to model the flow of control that characterize the behavior of the system as a whole, including use cases, patterns, mechanisms, and frameworks, or the behavior of the class or an individual operation. Whereas classes, interfaces, components, nodes, and their relationships model and aspects of your system interactions model as a dynamic aspects. When you model an interaction, you essentially build a storyboard of the actions that take place among the set of objects. Techniques such as a CRC technique, CRC cards are particularly useful in helping you to discover and think about such interactions. So, set the context of interactions, whether it is system as a whole, a class, or individual operation. Set the stage of interaction by identifying which objects play a role. Set their initial properties, including their attribute, values, state, and role. If your model emphasizes on structural organization of the objects, identify the links that connect them relevant to the paths of communication that take place in this interaction. Specify the nature of links using UML's standard stereotypes and constraints as necessary. In time order, specify messages that pass from object to object as necessary. Distinguish different kinds of messages, include parameters and returns values to convey necessary details of their interaction. Also, to convey the necessary details of these interaction, adorn each object at every moment in time with state and role. So, in this example, set object that interact the context, publish and subscribe the mechanism. So, there are three objects P for stock quit publisher, S1 and S2 are these are objects. So this is a class and S1 P is a class and S1 and S2 these are the objects. So attach S1 of this class P, attach S2 of this class P. So notify itself, then update to S1. Whether it is updated, then get state from S1 to P. Similarly, update towards S2. Whether it is updated, then get state from S2 to P. There is a message from this object, or this is communication within objects and class. So this is a semantically sequence diagrams. So first, this sequence diagram, there is a first this same S1 and S2 two objects of class P. So first attach S1, second message from S2 attach S2, then third notify itself, then fourth update, fifth update, then sixth from S1 to again P, that is get state, seventh again S2 to P get state. So this is a sequence diagram. You can draw any way, simple way, by using this way or by using this way. So what we have studied, hints and tips for interaction. When you model interaction in UML, remember that every interaction represents a dynamic aspect of society of objects. A well structured interaction is a simple and should encompass only those objects that work together to carry out some behavior. bigger than the sum of all these elements. A well-structured interaction has a clear context and may represent the interaction of the objects in the context of the operation, a class, or the system, or a whole. A well-structured interaction is efficient and should carry out its behavior with the optimal balance of time and resources. A well-structured interaction is adaptable and elements of the interaction that are likely to change should be isolated so that they can be easily modified. A well structured interaction is understandable and should be straightforward, involving no hacks, hidden side effects, or, of course, semantics. So, when you draw interaction in UML, select an emphasis for the interaction. You can emphasize either the ordering of messages over the time or sequencing of messages in the context of structural organization of the objects. You cannot do both in at the same time. So show when you draw interaction the UML show only those properties of each object such as attribute values, roles, state that are important to understand the interaction in the context. When you draw an interaction in UML, show only those properties of each message, such as its parameters, concurrency semantics, and return value, that are important to understanding the interaction of the content in the context. So this part is completed. Interaction part is completed here. Now, next part is use cases. We'll see in detail. Then, in this chapter, we'll study use cases, actors, include and extend, modeling as a behavior of an element, realizing use cases with collaborations. So, no system exists in isolation. Every interesting system interacts with human or automated actors to use that system for some purpose. For example, suppose you want to sum money from your account. There are two ways. Either you go towards ATM or in the respective bank. So here ATM acts as actor like a human. So here sentence every interesting system interacts with human or automated actor that use the system for some purpose, and those actors expect that system to behave in predictable way. Use case specifies the behavioral of the system or part of system and is a description of set of sequences of the actions including variant which a system performs to yield an observable result of the value to an actor. You apply use case to capture the intended behavior of the system you are developing without having to specify how that behavior is implemented. Use cases provide a way for your developers to come to a common understanding with your system's end users and domain experts. So in addition, use cases serves to help to validate your architecture and to verify your system as it evolves during the development. As you implement your system, these use cases are realized by collaboration, whose elements work together to carry out each use case. Well structured use cases denote essential system or subsystem behaviors only and are neither overly general nor too specific. One key factor in increasing use cases such as these is that you do so without specifying how the use cases are implemented. In UML, all such behaviors are modeled as use cases that may be specified dependent of their realization. A use case is a description of set of sequence of actions. A use case is a description of set of sequences of actions including variants that a system perform to yield an observable result of the value to an actor. There are number of important parts in this definition. So use case describes a set of sequences in which a sequence represents interaction of these things outside the system, that is its actors, with the system itself, that is key of abstractions. So these behaviors are the effect of the system level functions that you use to visualize, specify, construct, and document the intended behavior of your system during the requirement capture and analysis. A use case represents a functional requirement of your system as a whole. For example, one central use case is a bank process of loans. See in this figure, example of bank processor loan. Here, loan officer acts as actor. This is the use case. For this use case, name is process the loan. This is the loan officer. These are the names. Loan officer, process loan. These are the names. The elliptical shape is known as use case and the human like structure is known as actor. So use case involves interaction of actors and the system. An actor represents the coherent set of roles. So actor may play different roles, maybe sometimes as a customer, maybe sometimes as a manager, maybe sometimes as a developer, maybe sometimes as a user. So an actor represents a coherent set of roles that users of use cases play with when interacting with these use cases. Actors can be human or they can be automated systems. In case of ATM machine, actors act ATM machine. When you draw money from ATM, so ATM acts as an actor. So it may be actor may be automated system. For example, in modeling bank represents loan involves among their other things the interaction between customer and loan officer. So in this figure there is a shows the actor role of the customer and loan officer. So same actor acts as a loan officer as well as a customer. So a use case may have variant in all interesting systems. You shall find use cases that are specialized versions of other use cases that are included as a part of other use cases, and use cases that are extend the behavior of other core use cases. So you can factor the common reusable behavior set of use cases by organizing them according to these three kinds of relationships. For example, in a modeling bank, you will find many variations among the basic use case of processing loan, such as a different processing a jumbo mortgage versus small business loan. So, for the processing loans, there are two different types of loans: mortgage loan or small business loan. In each case, however, these use cases share some degree of common behavior, such as use case of qualifying customer for a loan or and a behavior that is a part of processing every kind of loan. A use case carries out some tangible amount of work from the perspective of the given actor. A use case does something that's of a value actors such as calculate the result, generate a new object, or change the state of another object. For example, in modeling bank processing, loan results in the delivery of an approved loan manifest in a pipeline of money handed to the customer. So use cases applied to a subsystem are excellent sources of regressions tests. Use cases applied to the whole system are excellent sources of integration and system tests. So, as shown in figure, UML provides graphical represents of use case and actor. This notation permits to visualize use case apart from the realization and in context of other use cases. So use case is denoted by elliptical shape, whereas the actor is denoted by a human-like structure, whether it acts as a human or automated system. So what are the terms and concepts regarding the use case? So use case is a description set of sequence of actions including variants that system performs to yield an observable result of the value to an actor. So graphically use case is rendered as ellipse. As shown in figure, these are the ellipse. Ellipse shows known as elliptical shapes. This ellipse or elliptical shape shows known as the use case, and use case these are the simple names: validate, user, place order. These are the simple names. This is a path name. Path name includes the scope resolution operator, sensors scope resolution operator, calibr- calibrate location. So in path name there is a scope resolution operator, whereas a simple name there is a simple name, there is no any other operator. So every use case must have a name that distinguish from each other. A name is textual string, or name is alone known as a simple name, or path name in use case name prefixed by the name of package in which the use case lives. So use case name may be a text consist of any number of letters, numbers, or most punctuation marks except for marks such as colon, except colon, which is used for separate common name and name of including package. So may continue where several lines. In practice, use case names are short, active words, phrases naming some behavior found in the vocabulary of the system you are modeling. Then use case and actors. An actor represents coherent set of roles. The users of the use cases plays when interacting with these use cases. Typically, an actor represents a role that a human or a hardware device or even others another system plays with the system. For example, if you work for a bank, you might be a loan officer and you do your personal banking there as well. You will always play the role of customer. Whether you are bank officer and you want to some money sometimes or that times you require to play role of customer. So an instance of an actor therefore represents individual interacting with the system in a specific way. So although you will use actors in your models, actors are not actually part of system. They live outside the system. So see in this figure, this is the commercial customer acts commercial customer, that is bank officer, and sometimes this bank officer wants money from his account, his or her account. Then he will act as a normal customer or normal actor. So actor acts as commercial customer or simple customer, behaves the same. There is a generalization or same figures. So when you use UML's extensibility mechanisms to stereotype an actor in order to provide different icons that might offer a better visual cue for your purposes, actor may be concerned to use cases only by the association. An association between an actor and use cases indicates that the actor and the use case communicate with one another and each one possibly sending and receiving messages. Then there is a relation between use cases and flow of events. So use cases describe what a system or subsystem, class or interface does, but it does not specify how it is does. Use case describes the what a system, subsystem, class, interfaces does, but it does not specify how it is does. When you model, it's important that you keep clear the separation of concerns between the system outside and inside view. When you write this flow of events, you should include how and when the use case starts and ends. When you use case interacts with the actors and what objects are exchanged and the basic flow and alternative flows of the behavior. For example, in context of the ATM system, you might describe the use case validate user by following way. Okay, there is the main flow of events. So the use case starts when system prompts customer for PIN number. The customer can now enter PIN via keyboard. Customer commits the entry by pressing enter button. The system then checks PIN number to see if it is valid or not. If the PIN number is valid, the system acknowledges the entry, thus the ending of use case. So the customer then exceptional flow of events. The customer can cancel transaction at any time by pressing the cancel button, thus restarting the use case. No changes are made to the customer's account. Exceptional flow of events. The customer can clear PIN number anytime before committing it and re-enter a new PIN. Exceptional flow of events. If the customer enter invalid PIN number, the use case restarts. If this happens 3 times in a row, then system cancel the entire transaction, preventing the customer from interacting with the ATM for 60 seconds. Now it is 24 hours. So you can specify the use cases flow of events in a number of ways, including informal structure text, such example above, the formal structure text with pre or post conditionals and the pseudocode. Typically, you will use one sequence diagram to specify use cases main flow, variants of the diagrams to specify use cases exceptional flow. So it is desirable to separate main versus alternative flow because a use case describes set of sequences, not a just single sequence. It would be impossible to express all details of an interesting the use case in just one sequence. Each sequence is called a scenario. Scenario is specific sequence of actions that illustrate the behavior. Scenarios are useful to use cases as instances are to the classes, meaning that a scenario is basically one instance of a use case. There is an expansion factor from use case to a scenario. A most modestly complex system might have a few dozen of use cases that capture its behavior. Each use case might expand out to the several dozens of scenarios. For each use case, you will find primary scenario which define essential sequence and secondary scenario which defines alternative sequence. So what is the relation between use cases and collaborations? Use cases captures intended behavior of system, subsystem, class or interface you are developing without having to specify how that behavior is implemented. That is the important separation because of the analysis of the system should which specifies the behavior should as much as possible not be influenced by implementation issues such as specify how that behavior to be carried out. Ultimately, however, you have to implement your use cases and you do so by creating a society of classes and other elements that work together to implement the behavior of use cases. This society of elements, including both its static and dynamic structure, is modeled in UML as a collaboration. So this figure shows you can explicitly specify the realization of use case by the collaboration. Most of time you can most of time though a given use case is realized by exactly one collaboration, so you will not need to model these relationships explicitly. So the use case diagram is denoted by elliptical shape, whereas collaboration diagram is denoted by dotted elliptical shape. And there is a realization from collaboration to use case. Use case is place order and collaboration is order management. So although you may not visualize this relationship explicitly, the tools you use to manage your models will likely maintain these relationships. Finding the minimal set of well-structured collaborations that satisfy the flow of events specified in all the use cases of the system is focus the system's architectures. So you can organize use cases by grouping them in a package in the same manner in which you can organize classes. You can also organize classes by specifying generalization, include, extend relationships among them. You can also apply these relationships in order to factor common behavior by pulling such behavior from other use cases that it includes, and order by to factor variance by pushing such behavior into other use cases that extend it. Generalization among the use cases, just like a generalization among the classes. Here it means that the child use case inherits the behavior and meaning of the parent use case. A child may add or override the behavior of its parent. A child may be substituted any place the parent appears. Both the parent and child may have concrete instances. For example, banking system, you might have use case validate user, which is responsible for verifying the identity of the user. You might be then have two specialized children of these use case, that is a check password and retentional scan, both of which behave just like a validate user and may be applied anywhere validate user appears, yet both of which add their own behavior. The former by checking textual password, the latter by checking unique retina patterns of the user. So as shown in figure, the generalization among the use cases is rendered as solid circles. Solid directed lines indicates that the generalization with large open overhead. These are the generalizations. For previous slides example, we have seen validate user in case of banking. There is a checking password and rotational scan. This open arrowhead is generalization. Solid lines indicates that the generalization, whereas this is extended relationships. These include the extended relationships. These are the extended points. So, an include relationship between a use case means that the base use cases explicitly incorporates the behavior of other use case at the location specified in the base. The included use case never stand alone but only is only instantiated as a part of some larger base that includes it. You can think of include as a base use class pulling behavior from the supplier use case. So you use an include relationship to avoid describing the same flow of events several times by putting the common behavior in use case of its own. The include relationship is essentially an example delegation. You take the set of responsibilities of the system and capture one it in one place. Then let all other parts of the system, that is other use cases, include new aggregation of the responsibilities whenever they need to use that functionality. You render an include relationship as a dependency stereotyped as include to specify the location in the flow of events in which the base use cases include the behavior of another. You simply write include followed by the name of use case you want to include, as in following flow track order. So obtain and verify the order number, include validate user for user each user part in order, query in status, and then report back to the user. An extended relationship use cases mean that the basic use case implicitly incorporates in the behavior of another use case at a location specified indirectly by extending use case. The base use case may stand alone, but under certain condition, its behavior may be extended in the behavior of another use case. This base use case may be extended only at certain point called not surprisingly its extension point. You can think of extend as extension use case pushing behavior to the base use case. You use extend relationship to model part of use case. The user may see an optional system behavior. In this way, you separate the optional behavior from mandatory behavior. You may also use an extend relationship to model a separate subflow that is executed only under given conditions. Finally, you may use extend relationship to model several flows that may be inserted at a certain point governed by explicit interaction with an actor. So what are the other features of use case? Use cases are classifier. So they may have attributes and operations that you may render just as for classes. You can think these attributes as objects inside the inside the use case that you need to describe its outside behavior. Similarly, you can think these operations as the actions of the system you need to describe the flow of the events. These events and the operations may be used in your interaction diagrams to specify the behavior of these use case. As a classifier, you can also attach the separate machines to use cases. You can use state machines as yet another way to describe the behavior represented by the use case. So common modeling techniques, that is modeling behavior of an element. So there are three common modeling techniques. So most common things you will apply use cases to model the behavior of an element, whether it is a system as a whole, subsystem or class. When you model behavior of these things, there are important. You focus what the element does, not how it does it. So applying these cases, the elements in this way important, there are three reasons. First, by modeling the behavior of element with use cases, you provide a way for domain expert to specify its outside view to a degree sufficient for developers to construct its inside view. Use cases provide a forum of your domain experts, end users, and developers to communicate to one another. Second, use cases provide a way for developers to approach an element and understand it. A system, subsystem, or class may be complex or full of operations and other parts. By specifying an element's use cases, you help users these elements to approach them in a direct way according to how they are likely to use them. In the absence of such use cases, users have to discover on their own how to use those elements. Use cases let the author of the element communicate his or her intent about how the element should be used. And third, use cases serves as basis for testing each element as it evolves during development. By continuously testing each element against its use cases, you continuously validate its implementation. Not only do these use cases provide a source of regression tests, but every time you throw a new use case at an element, you are forced to reconsider your implementation to ensure that these elements is resilient to change. If it is not, you must fix your architecture appropriately. So to model the behavior of an element, identify the actors that interact with the element. Candidate actors include groups that require certain behavior to perform their task or that are needed directly or indirectly to perform elements function. Organize actors by identifying general or more specialized roles. For each actor, consider the primary way in which the actor interacts with the element. Consider also interactions that changes the state of the elements or its environment or that involve a responsible of some event. Consider also the exceptional ways in which other actor interact with the element. Organize these behaviors as use cases applying includes and extend relationships to factor common behavior and distinguish exceptional behavior. So for example, the retail system will interact with customers who place the track orders. In turn, the system will ship orders and bill the customers. The figure shows you can model the behavior such system declaring these behaviors of use cases, that is place order, track order, ship order and bill customers. So this is the valid customer place order, track order, then ship order. So ship partial order is extended whether the customer is validate, then bill the customer. So common behavior can be factorized out the validate customer and variants ship partial order to be distinguished well. So for each of these cases, you should include a specification of behavior either by text, state machine or interactions. As your model gets bigger, you will find that many use cases tend to cluster together in groups that conceptually or semantically related. In the UML, you can use packages to model these clusters of the classes. So what we have studied, when you model the use cases in UML, every use case should represent some different and identifiable behavior of the system or part of the system. So a well structured use case name a single identifiable reasonably automatic behavior of the system as part of the system. Factors common behavior by pulling such behavior from other use cases. So factors variant by pushing such behavior into other use cases that extend it. Describe the flow of events clearly enough for an outsider to easily understand it. A well structured use case is described by minimal set of scenarios that specify the normal and variant semantics of the use case. When you draw use case in the UML, show only those use cases that are important to understand the behavior of the system or part of the system in its context. Show only those actors that are related with these use cases. So we stop here.